Section 7.3, Polynomial and Rational Inequalities. In this section, we're going to see how to solve polynomial and rational inequalities graphically and algebraically. For our first example, we will solve graphically x to the fourth minus 5x squared plus 4 is greater than or equal to 0. So to do this, I will graph y equals x to the fourth minus 5x squared plus 4 on the calculator, and I'm going to find some important points on the curve, the zeros, the x-intercepts, and then use the rest of the curve to help me answer the statement. Alright, so y equals x to the fourth minus 5x squared, and it's plus 4. Alright, and let me check my window. I'm on the standard window. Let's just graph from the standard window. Alright, and actually that gives me a pretty good picture of the curve. We know that since it's of the degree 4, we should have at most 3 turning points, and I do see 3 turning points, so there will be no more turning points on the curve. Alright, I'm going to move in a little bit on the curve here. Let me change my window from -5 to 5 on the x's. Alright, so that's a little bit of a easier picture to work with. And it looks like I have 1, 2, 3, 4 x-intercepts, and I'm just going to go ahead and calculate a couple of them. Let me calculate the leftmost x-intercept, and enter, and move to the right of it, hit enter a second time, move back towards the middle. And so I have a 0 at -2, and the other ones look to be at -1, 1, and 2. Let me just trace and check. So let me trace -1. So y equals 0, -1 is a 0. Let me trace 1. 1 is a 0, and let me trace 2, and 2 is a 0. Alright, so there's that graph, and again, this is, we have zeros at -2, -1, 1, and 2. Now, we were asked to solve graphically where the function was greater than or equal to 0. Well, we know it's equal to 0 at -2, -1, 1, and 2. Now, where is it greater than 0? Well, all of these points are greater than 0, have y values greater than 0, and these points have y values greater than 0, and these points have y values greater than 0. Now in terms of x, smash those points to the x-axis, and we would have this interval, and this interval. So then the solution of the inequality, I'll write using interval notation, would be -infinity to -2 bracket union bracket -1 to 1 bracket union bracket 2 to infinity. So that's where there are solutions of this inequality. Any of those regions, the graph was above y equals 0 or equal to y equals 0, and so we just describe them in terms of x using interval notation. Alright, here's another example. We're asked to solve graphically. -x to the fourth is greater than 32x minus 16x squared minus 2x cubed. Alright, I'm going to get this to... I want to get one side of this to 0. And so it would be easiest to move this term over to the right. So I'm going to rewrite this as 0 is greater than x to the fourth. I'm going to write this in descending order. Minus 2x cubed minus 16x squared plus 32x. And so I'll graph this as my y equals, and again I'll compare it to 0. Alright, so I've got my calculator, and my y equals is x to the fourth minus 2x to the third minus 16x to the second plus 32x. Make sure I type that in correctly. That looks good. And I'll go back to my standard window by hitting zoom 6. Alright, and it looks like I've got 1, 2, 3, 4 x-intercepts. Let me adjust the window. It looks like it's going way above y equals 10 and way below y equals negative 10. So let me adjust my window. I'll keep my x's as they are from negative 10 to 10, and let me adjust the y's to go from negative 50 to 50 and see if that gives me a better picture. I'll change my scale to tens on the y-axis. Alright, so that's a little bit of a better picture. Let me adjust the window just a little bit more. Let me change the y minimum to, how about negative 80? Just a little more. How about negative 110? Alright, and so there's a good picture of the curve. Now it looks like I have 1, 2, 3, 4 x-intercepts. Let me just double check and make sure that they're whole numbers. Let me trace negative 4. Negative 4 is 0. Let me trace 0, 0, 0, 2, 2, 0, and 4. Alright, so we have those 4 points. Alright, let me grab that graph and put it on screen so we can annotate it a little. Alright, so there's the graph. And we have x equals 4, x equals 0, x equals 2. I'm sorry, that should have been a negative 4 on the left, and x equals 4. Now, in this case, though, we have a strictly less than inequality. Since it's a less than inequality, it's not an or equal to inequality. What I'm going to do is I'm going to put open points here instead of solid points. I'm going to put open points at all of those x-intercepts. What that's going to remind me is I can't include those as endpoints. I can't include the endpoints as solutions because that's not equal to. Now, I want, if I think about what I've written here, I have 0 is greater than y, so turn that around. I want the y values to be less than 0. So let me shade where the y values are less than 0. All right, so these points have y values less than 0, and these points have y values less than 0. And so smashing that to the x-axis, I would have this interval and this interval. So then my solution for the inequality is from negative 4 to 0, but I can't include the negative 4 or the 0. So I'm going to use parentheses. Union 2 to 4, and again with parentheses. So there's how we would solve these graphically. Now let's take a look at how we would solve using symbolic or algebraic techniques. To solve a polynomial inequality algebraically, we're going to first write the given inequality in the form f of x is less than 0, greater than 0, less than or equal to 0, or greater than or equal to 0 as appropriate. So basically we want to get all the terms on one side of the inequality and we want to compare to 0. We replace the inequality symbol with an equal sign and we solve f of x equals 0. We'll plot the solutions from step 2 on the number line using a solid dot if the inequality is a less than or equal to or a greater than or equal to. And we'll use an open circle if we have a strictly less than or strictly greater than. Then we will test a point in each interval to see whether it satisfies the inequality. Then the solution will consist of the intervals that will satisfy the original inequality. This is actually quite similar to what we did in a previous chapter when we were solving quadratic inequalities. Just now we might have more x-intercepts to consider and more intervals to consider. Solve algebraically 2x cubed is less than or equal to 3x squared plus 5x. So the first thing I'm going to do is I'm going to compare this to 0. So I would rewrite this as 2x cubed minus 3x squared plus 5x is less than or equal to 0. Now I'm going to solve the related equation 2x cubed minus 3x squared plus 5x equals 0. I know how to solve this equation. I'm going to use factoring. I see a factor of x, so I can write this as x by 2x squared minus 3x plus 5 is equal to 0. And I can actually continue to factor this. X times, let's see, that's a 2x and an x, and I need a 5. Let's see, I think I need a 5 here and a 1 here. That would give me a 2x squared, a 2x, a 5x, and a 5. And to get a negative 3x, I need a minus 5 and a plus 1. That would give me a negative 5x and a plus 2x, which does give me the negative 3x. So that's the correct factored form. And this is still equal to 0. So then, setting the factors to 0, x is 0, 2x minus 5 is 0, which implies x equals 5 over 2. And x plus 1 equals 0, which implies that x equals negative 1. So those are my solutions of the equation. 0, 5 halves, and negative 1. So now we go to a number line. And I plot those 3 points on the number line in numerical order. So I'm going to put negative 1 here, 0 here, and 5 halves here. And now I'm going to test in each of these 4 intervals. I pick a number in each of those 4 intervals, and I'm going to test into the easiest form to work with, which I think is the factored form. So I'm going to test in x by 2x minus 5 by x plus 1. And I really should have solid points at negative 1, 0, and 5 halves, because my inequality is an or equal to inequality. All right, my inequality is an or equal to inequality. So now let me test a value that's less than negative 1. How about negative 2? So I'm testing in the expression x by 2x minus 5 by x plus 1. And I'm going to let x equal negative 2. So that would give me negative 2. 2 times negative 2 minus 5, that's negative 9. Negative 2 times 1 is negative 1. Negative 2 plus 1 is negative 1. I have a negative times a negative times a negative. That's a negative. Now, all right, so I'll just write negative there. Testing between negative 1 and 0. How about a negative 1/2? Letting x equal negative 1/2. That would be negative 1/2. 2 times negative 1/2 minus 5, that's 2 times a negative, that's a negative, plus a minus 5, that's going to be a negative number. Negative 1/2 plus 1, that's a positive number. Negative times a positive is a positive. Testing between 0 and 5 halves, how about x equals 1? So that would give me a 1 times 2 times 1 minus 5, that's a negative, and 1 plus 1 is a positive. So that would give me a negative. And finally, testing a value greater than 5 halves, how about 3? That would give me 3 by 2 times 3 is 6 minus 5 is positive, and 3 plus 1 is positive. Positive, 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 that's a positive. Now, I wanted the 2x cubed minus 3x squared plus 5x to be less than or equal to 0. So I would shade wherever the result came back negative. So then my solution, right, the solution of this inequality would be the interval from negative infinity to negative 1, and I can include the negative 1 union the interval from 0 to 5 halves, and I can include both of those boundaries. All right, here's another example. X cubed is greater than 6x squared minus 9x. I will again first rewrite this as x cubed minus 6x squared plus 9x is greater than 0. And I will solve the equation x cubed minus 6x squared plus 9x equals 0. I can factor out the x, so I have x by x squared minus 6x plus 9 is 0, and x squared minus 6x plus 9 factors as x minus 3 times x minus 3, or x minus 3 squared. So then x equals 0, or x minus 3 equals 0. So x equals 0, and x equals 3. So there's my two solutions of the equation, and I will plot those on the number line. Here's 0, and here's 3. And I'm going to use open points at 0 and 3, because it was a strictly greater than inequality, which means I will not be able to use those boundary points, because at the boundaries the output would be 0, which is not greater than 0. Alright, let me test. There's my 3 test points, and I'm going to test into x by x minus 3 squared. So how about I test negative 2? So if x equals negative 2, then I would have negative 2 times negative 2 minus 3 squared, which is a negative times, now negative 2 minus 3 is a negative 5, which squared is positive. And so I have a negative times a positive, which is negative. Let me test between 0 and 3. How about x equals 2? If x equals 2, I would have 2 times 2 minus 3 squared, and so that's a positive times a positive, which is positive. And how about x equals 4? Testing x equals 4, I would have 4 times 4 minus 3 squared, and so that would be a positive, and then 4 minus 3 is 1, and 1 squared is a positive. Now, I wanted x cubed minus 6x squared plus 9x to be greater than 0. So I will shade wherever it's positive. I shade the interval from 0 to 3. I shade the interval from 3 to infinity. So then, how would I write the solution? I've shaded from 0 to 3, so 0 to 3, union, and I've shaded from 3 to infinity. I cannot write, I cannot write this, because this now includes the point where x equals 3. But I can't include x equals 3, because when x is 3, x cubed minus 6x squared plus 9x is equal to 0, which is not greater than 0. Alright, so I have to write 0 to 3, union 3 to infinity. Now let's consider rational inequalities. So we have 2x minus 4 over x squared minus 16 is greater than 0. So, like I did with the polynomial, I'm going to graph this as my y equals, and I'm now going to consider, I want to find where the points are greater than 0. So I want to find the points above the x-axis. Alright, so there's my calculator, and let me write this as 2x minus 4. Notice how I'm using parentheses around the numerator, over x squared minus 16. Notice again how I'm using parentheses around the denominator. And I'll go back to the standard window. Alright, it looks like I have a couple of vertical asymptotes at positive and negative 4. And it looks like I have one x-intercept. So let me adjust my window a little bit. I'm going to change my window to that negative 9.4 to 9.4 to get a nicer picture. Alright, so I can see the asymptotes. And let me find that x-intercept. The x-intercept appears to be somewhere between 0 and 3. Let me calculate that x-intercept. So it appears to be pretty close to 2, actually. And actually, I think it should be 2 based on what I see in the numerator. And so I do see a 0 when x is 2. Alright, so let me grab the graph and put it on screen so we can annotate it. Alright, so let's see. We have vertical asymptotes at -4, +4, and we have an x-intercept at 2. Notice that the sign can change at asymptotes and at the x-intercept. Now, we wanted the points where the y value was greater than 0. Where is the y value greater than 0? Well, these points have y values greater than 0, and these points have y values greater than 0. Smashing that to the x-axis, we would have this interval and this interval. So then the solution of the inequality would be from -4 to 2 union 4 to infinity. Alright, and those 4's again are coming from the asymptotes. We have an asymptote at x equals -4. We have an asymptote at x equals +4. Let's see another example. Solve graphically. X plus 1 over x plus 2 is less than or equal to 0. Let me bring up my calculator, and I'll clear out the old stuff. And we have x plus 1 over x plus 2. Notice again how I'm using parentheses. And let me graph that on my window. And it looks like I have an asymptote, a vertical asymptote at x equals -2. And I have a x-intercept at x equals -1. Let me trace -1 just to verify that. -1, 0. Alright, let me grab the graph and put it on screen. Alright, so I graphed this as my y equals, and I have a vertical asymptote at x equals -2, and I have an x-intercept at -1. Now, since I have a less than or equal to, since it's an or equal to, I will use a solid point here at -1. Now, I wanted the y values to be less than 0, and the y values are less than 0 only in this region, which does continue down all the way along following the asymptote. And so smashing that to the x-axis, we have this interval. And so the solution for this inequality would be the interval from -2 to -1. I cannot include the -2 because that's an asymptote. I do include the -1. It's an x-intercept, and I had an or equal to on the inequality. Notice again that the sign could only change at the x-intercepts and at the asymptote, right? If we follow the curve, notice the curve was positive, right? The y values were positive, and then at the asymptote, jumped to negative, and then at the x-intercept, changed back to positive. So the sign can only change at asymptotes and at x-intercepts. So now, solving a rational inequality algebraically. First thing we do, like we did with the polynomials, is we write the given inequality so that we're comparing it to 0 as appropriate. Now, if we have more than one rational expression on the left-hand side of the inequality, we combine them to a single fraction. We then determine any values whether the numerator or the denominator are 0. These will be critical values that will determine intervals on the number line. So those correspond to the x-intercepts and the asymptotes of the graph, the vertical asymptotes. We plot the solutions from step 2 on the real number line. For the numerator, we're going to use solid dots if the inequality was less than or equal to or greater than or equal to, and we use open circles if the inequality was strictly less than or greater than. We exclude any values that would make the denominator equal to 0. And so we always use an open circle for critical values related to the denominator. Then we select test points, and we see which regions satisfy the original inequality. Alright, so let's solve algebraically x minus 1 over x plus 1 equals 0. Alright, so notice it's already compared to 0. So the first thing I will do is set x minus 1 to 0, which implies that x equals 1. So that's a critical value from the numerator. I will set the denominator to 0, which implies x equals negative 1. Alright, so we have these two critical values. Now since this is a strictly less than inequality, we would have open points at both of these. Test the regions. So let me test negative 2. So then I would have negative 2 minus 1 over negative 2 plus 1. That's a negative over a negative, which is positive. So I have a positive in the first interval. Let me test x equals 0. Then I would have 0 minus 1 over 0 plus 1. That's a negative over a positive, which is negative. And I'll test x equals 2 in the third interval. Then that would give me 2 minus 1 over 2 plus 1, which is a positive over a positive, which is positive. Now, I wanted x minus 1 over x plus 1 to be less than 0, so I want the function's output to be negative. I shade that region on the number line, and I write my solution using interval notation. I will write that the solution goes from negative 1 to 1, and I would put parentheses on both since I have open circles for both. Alright, here's another example where I have to solve algebraically. 5 minus x over x squared minus x minus 2 is greater than or equal to 0. The inequality is already comparing to 0, so I will set the numerator to 0. 5 minus x equals 0, and so solving that for x, I find that x equals 5. Now, since this is an or equal to inequality, that's going to get a solid point. Setting the denominator to 0. X squared minus x minus 2 equals 0. That factors as x plus 1 by x minus 2. So x plus 1 is 0, which means x equals negative 1. X minus 2 equals 0, which means that x equals 2. And since these are critical values from the denominator, these will get open points. Draw my number line with my critical values. Let's see, I'll put, there's negative 1 and 2 and 5. Let me put in my points here. 5 gets a solid. Negative 1 and 2 get opens. And now I'll test each interval. So let me test, how about negative 2? And I'm going to test into the factored form. I'm going to test into 5 minus x over x plus 1 by x minus 2. Because that's easy to determine if we have positives or negatives. And that's all we really care about. Is it positive or negative? Alright, so now let me test x equals negative 2. So that would give me 5 minus negative 2, that's a positive, over negative 2 plus 1 is a negative. Negative 2 minus 2 is a negative. So I have a positive over negative times a negative is a positive. That's a positive. Then I test value between negative 1 and 2. How about I test 0? If x equals 0, I have 5 minus 0, which is positive, over 0 plus 1, which is positive, times 0 minus 2, which is negative. So let's see, that's going to end up being negative. Let me test between 2 and 5. How about I test x equals 3? Testing x equals 3, I would have 5 minus 3, which is positive, over 3 plus 1, which is positive, times 3 minus 2, which is positive. All positive, so that's positive. And how about x equals 6? Testing x equals 6, 5 minus 6 is negative, over 6 plus 1 is positive, 6 minus 2 is positive. Negative over a positive is negative. Alright, we wanted the function to be greater than or equal to 0, so I'm going to shade wherever I ended up with positives. So positive and positive, and then write the solution using interval notation. So solution would be from negative infinity to negative 1, parenthesis, union, parenthesis 2, comma 5, bracket. Solve algebraically. X minus 4 over x plus 3 is less than or equal to 6. Well, the first thing I would do is subtract 6 so I can compare to 0. So I have x minus 4 over x plus 3 minus 6 is less than or equal to 0. Now, to use the technique that we've been using in the previous examples, I need to rewrite that 6 as a fraction so I can combine these fractions to a single fraction. Well, 6 is the same as 6 over 1. And so to have a common denominator of x plus 3, I will multiply both numerator and denominator of that fraction by x plus 3. So now I have x minus 4 over x plus 3, subtract 6x plus 18 over x plus 3 is less than or equal to 0. Now subtracting, now be careful here, remember when you subtract, you're subtracting that entire numerator. So I have x minus 6x, so that's a negative 5x, and now I have a negative 4 minus 18, that's a minus 22, over x plus 3 is less than or equal to 0. Now, finding the critical values. Setting the numerator to 0. Negative 5x minus 22 is equal to 0. I would add 22 and divide by negative 5, and x equals negative 22 over 5. And this will get a solid point because it's an or equal to inequality. Setting the denominator to 0. X plus 3 is equal to 0 implies x equals negative 3, and this would get a open point because it's a critical value from the denominator. Number line. I got two values, critical values. Negative 22 fifths, that's negative 4 and 2 fifths, so that would go here because that's less than negative 3. Alright, and I will test into negative 5x minus 22 over x plus 3. Alright, so let me test a number less than negative 4 and 2, let's say negative 6. If x equals negative 6, then I'd have negative 5 times negative 6, that's 30 minus 22, that's a positive. over negative 6 plus 3 is a negative, negative. Let me test somewhere between negative 22 over 5 and negative 3. How about negative 4? Testing negative 4. I'd have negative 5 times negative 4. That's 20 minus 22. That's a negative. Negative 4 plus 3 is a negative. Negative over a negative is a positive. And testing a value greater than negative 3. How about 0? Testing x equals 0. I'd have negative 5 times 0. Well, that's 0 minus 22 is negative. Over 0 plus 3 is positive. And negative over a positive is a negative. Now, going back to this form, we wanted negative 5x minus 22 over x plus 3 to be less than or equal to 0. So I'm going to shade the negatives. Now I forgot to put my solid points and open points here, so I have a solid point at negative 22/5 and an open point at negative 3. So writing the solution, I would have negative infinity to negative 22/5 bracket union parenthesis negative 3 to infinity parenthesis. Alright, one more example. X minus 6 over x minus 3 is less than or equal to x plus 4 over x. Again, first thing I'm going to do, I need to get this to 0, compared to 0. So I'll rewrite this as x minus 6 over x minus 3 minus x plus 4 over x is less than or equal to 0. Now to combine these fractions, I need a common denominator. So I'll multiply both numerator and denominator of the first fraction by x, and numerator and denominator of the second fraction by x minus 3. So that gives me x minus 6 times x, that's x squared minus 6x over x by x minus 3, minus x plus 4 by x minus 3, that's x squared plus x minus 12, over x by x minus 3 is less than or equal to 0. Subtracting these fractions, and remember when I subtract, I'm subtracting the entire numerator, so I have to think distributive property there. I have the common denominator of x by x minus 3, and it's still less than or equal to 0. I have an x squared minus an x squared, so that's a 0. I have a negative 6x minus x. That's a negative 7x. And I'm subtracting a negative 12. That's a plus 12. So I have negative 7x plus 12 is less than or equal to, over x by x minus 3 is less than or equal to 0. Setting the numerator to 0. Negative 7x plus 12 equals 0. Subtracting 12, dividing by negative 7, x equals 12 over 7. And since this is an or equal to inequality, this will be a solid point. Setting the denominator to 0. X by x minus 3 equals 0. This implies that x equals 0, or x minus 3 equals 0, which implies that x equals 3. And these would be open points, since they're critical values of the denominator. Now 12 over 7 is 1 and 5/7. So between 1 and 2. So on my number line, I would put 0 here. Let's put 12 over 7 here, and 3 here. So I have to test 4 intervals. Let me remember to put my solid and open points down. I have a solid point at 12/7, and open points at 0 and 3. I will test into negative 7x plus 12 over x times x minus 3. Alright, let's test negative 1. For the first interval, negative 7 times negative 1 is 7 plus 12 is positive over x is negative 1. That would be a negative times negative 1 minus 3 is a negative. Positive over a negative times a negative, that's a positive over a positive, which is positive. Testing between 0 and 12/7, I'll use x equals positive 1. That would give me negative 7 plus 12, that's a positive, over positive times negative, that would be a negative. Between 12/7 and 3, let's use x equals 2. Negative 7 times 2 is negative 14, plus 12 is negative, over positive times 2 minus 3 is a negative, so that would be a positive. And finally, a value greater than 3, how about x equals 4? That would give me negative 7 times 4 is negative 28 plus 12. That would be a negative over a positive times a positive, and so that would be a negative. Now we wanted the negative 7x plus 12 over x by x minus 3 to be less than or equal to 0, so I'll shade wherever negative. And writing the solution using interval notation, I would have from 0 to 12/7, and I can bracket the 12/7, union, parenthesis, 3 to infinity. All right, so that concludes the presentation for this section.